Okay, so the next speaker is Carlo Drioli from the University of Udine in Italy, and he's talking about time delay estimation for speaker localization using CNN-based parameterized GCC-FAT features.
Thanks. Hi. Hello to everyone. So I'm going to describe this study conducted with my colleagues Daniele Salvati and Gianluca Foresti from the Audiovisual Research Lab at the University of Udine. And problem addressed here is speaker localization in noisy and reverberant environments using a very compact microphone array, actually a two microphones array, with as a reference a common approach like a GCC-PHAT method. The problem addressed here is that FAT normalization, as is well known, emphasizes noise. It is known that FAT filtering helps in reverberant conditions, but at low noise conditions. When we have higher noise conditions, the performance decreases. So the point here is to find a solution for this particular conditions, which are, like to note, which are quite common in many nowadays critical application. One simple example is the one in which drones carries microphones for acoustic analysis, automatic acoustic analysis, or for surveillance, or for autonomy. And and if you think of aerial drones, for example, you may understand that the conditions are very critical in that case, where microphones are surrounded by propellers or engines. So the proposed solution is to use some augmented version of the GCC-FAT features as an input to a CNN component to see if the CNN component might learn how to use this redundancy to get better results. And so just a brief introduction to the background of the theory underlying GCC-FAT. We can refer to a signal model with microphone positions RM and source position RS, and the X in this case in the frequency domain is the signal recorded at microphones. HM is the transformer of the impulse response of the path of the propagation, and N here is the white Gaussian noise, mutually independent added at microphones. So acoustically, from acoustics, you can compute the delay at microphones, the delay of arrivals of the front of the waveform at microphones by this relation, which is proportional to the difference of the distance from source and microphones. And the problem here is how to estimate this delay, time of delay, by using the recorded signal. So GCC-FAT for a two microphone array in this case is specific to the two microphones array is shown here, where the FAT normalization is this term at the term at the denominator here, and it is intended to normalize the spectrum magnitude, so to better exploit the phase information. Just to recall also that once you have this function R, you can find the time domain estimation by a search, by a big search on this function, which is the weak point in this approach, and also recall that tau max is limited by the geometry of the array. Finally, just to recall also that when you have the time domain of arrival, you it's straightforward to also compute the angle, the direction of arrival of the source by simple geometric considerations. Okay. And so, as I said before, the problem here in this approach is the search of the maximum of this function. Forgot to recall that, to say that the k in this case is the frame of the speech signal. This is all performed on a frame by frame basis. Searching peaks is always a tricky method, and as you know, have issues, and it has issues mainly because of the fact that FAT is known to emphasize noise when the signal is affected by noise. It also emphasizes noise, which affects the peaking, of course, search. The point is that FAT seems to be a good approach in some conditions and not in others, or in some part of the spectrum, but not in others. So the idea, here's the proposal here, is to build a rich set of different FAT-weighted functions parameterized by this term beta, and to build this as the input of the CNN, which then will use this redundancy to select, hopefully, the best information to get the right result. To do this, we have to introduce this parameterized GCC function, which is, as you may have thought, it's the GCC function in which the normalization factor is weighted by a parameter beta, so that you have a GCC standard function when beta is 0, and you have a conventional FAT GCC function when beta is 1. So you can choose to build a matrix of input by selecting a different values of beta in a range 0, 1. In this case, we decided to use a value of about 10 different weighting values for beta, and I will return on this choice at the end when present the results. And then you have this matrix, which has the dimension, in this particular case, dimension 11, so B, which is the number of weighting parameters, by about 20, which is the number of the tau values that we are considering. We are considering this 20 values in this particular case because these are related to tau max, and for our given our specific geometrical configuration of the array, which is 20 centimeter spaced microphones, we have this kind of result. So just a few notes on the structure of the CNN. The CNN is built with 5 different layers made by 3 by 3 kernels and increasing number of filters in the first stages, so from 32 up to 512, followed by conventional batch normalization and ReLU. Then we have a final stage of three fully connected steps, and a final regression steps that that computes the value of the estimation, and this gives us also a mean square error based loss function. The assessment is conducted on several simulated signal-to-noise ratio and reverberant conditions. Then we have a simulated experiments in which we use a database from McGill University, the TSP speech database, which is made of 1,378 utterances, 23 speakers, 12 females, 11 males. Utterances length is 2 seconds on average, and it is recorded in anechoic conditions so that we add noise and generate reverb artificially. The training test subset is divided in a 70-30% split way. And the difference signal-to-noise ratio level were obtained by adding mutually independent wave white Gaussian noise in the range, so to obtain a range between -15 to +30 dB of signal-to-noise ratio. And the different reverberant conditions were obtained by using an image source model, so to have a resulting RT60 levels in the range 0, 1 second, 1 second. So the training of the CNN parameters was performed through the Adam method, and this is a quick look at the parameters. So learning rate, gradient decay factor of 0.9 squared, gradient decay factor 0.999, mini batch size 128, and number of epochs 50. The room dimensions were and positioning of the array and speaker were different for training and testing. This is a quick look at the different conditions for the training. Note that microphone positions are slightly different, and also speakers angle where spanned range -19 degrees in training, whereas during testing they were selected randomly in the room. And here I've showed you the result, the experimental result on the simulated data sets, and these are in terms of root mean square error and compared to conventional GCC-FAT. So we have this RMS E error when the signal-to-noise ratio is varied from -15 dB up to 30 dB for a fixed value of RT60 of 0.1 seconds. And you can see how the GCC-FAT, the proposed method actually outperforms the GCC-FAT estimations by about 0.08 milliseconds, and this is constant for all SNR values, whereas the difference is a little bit less for very low signal ratio. The same thing is obtained for different RT60 values, whereas the proposed method always outperforms the GCC-FAT by a similar amount in that case. In that case, signal-to-noise ratios were held constant at 30 and 5 dB respectively. So I mentioned before that we used a value of 11 for the parameter B, that is for the number of parameterized GCC function, and that's because we investigate what the performance difference at increasing of this parameter, and although we didn't investigate a very fine resolution interval, we saw that up to a certain threshold the things get better, but after this threshold that was 11 for us, things didn't change too much. So that's why we then kept this value for the experiment. So to conclude, we addressed speaker localization by compact array processing and hybrid GCC-FAT CNN, a computation scheme, and this proposal proven robust in noise and reverberant conditions and proved to have better results with respect to GCC-FAT. And just for the future work, as I mentioned, we have facilities to experiment with drones. And in fact, one of our future work on this particular research is using real data recorded from flying drones carrying microphones for detection and for localization in surveillance applications. And also some investigation will be done on how the CNN how the CNN exploit this information, this redundant information, to select the best GCC-FAT normalization and improve results. So that's all, I think, for me. And thank you very much.
Thank you. Any questions from the audience?
Yes, please.
Can you take the microphone? Where is it?
So actually, I have two questions.
Okay. So actually, I have two questions, if you don't mind. First, did you investigate to what angle improvement your results corresponds to?
Sorry? How
what
to improve?
Angle improvement, not the time delay, but what the localization error in
Angle.
Yeah, in degrees.
Okay, yeah, you're right. Well, these, if you convert time delay into angles, this improvement corresponds to up to 7-8 degrees for the best signal to noise ratios, down to a few degrees for the worst cases. And yes, recall we have a minus 90 to 90 range divided by in 20 different discrete values.
Okay, so it's quite a lot, thanks. Yeah. And the second is, do you think that you can use this method to a larger microphone array, for example, for SRP-FAT method?
Yeah, exactly. This is one thing that we wanted to do. Actually, we started by exploring this very compact array. We didn't yet look at larger arrays, but it's definitely in our schedule. Yeah.
Thanks.
Thank you very much.
So I think you said that you were exploring using this with aerial drones. Is that correct?
Yeah, that's correct. Yeah, not these specific algorithms yet. We've done it with different algorithms and used conventional GCC-FAT. And yeah, that's right.
So, well, the reason I'm asking is because I can imagine, let's say, in large warehouses that you could have, in large warehouses, you could probably have reverb as well. And your T60 values went from 0.1 100 milliseconds to 1 second. So you would expect some reverberation. But I'm guessing if you're flying outside, you're not going to have the reverb.
Yeah, that's right. But this is not always true. You have to consider also those circumstances in which outside means flying not too far from buildings. And in fact, this is one of the situations in which we had to deal with, because in our campus, spaces where we fly drones are very nearby, and building reverberation affects very much and also yeah, we are looking at noise indoor environments where reverberation and noise are very important.
Sorry.
Thank you.
If you applied to some real data, it would really be interesting, because I have to believe it's really challenging for the audio streams that you're getting.
Yeah, it is, and we have actual data already on other algorithms. So if you want, I can for sure send you all the previous results that we have on this.
Yeah, I'll just mention that in the forensics area, there's lots of audio that law enforcement have to collect for a fleeing criminal. And that type of audio is ideal to try and feed into this. And I've never seen anyone try to build a successful system for something like that.
That would be great to try on that.
Okay, we have one
Thank you.
last quick question, then we have to move on.
I also had a question that was in a similar thread as Dr. Henson was saying. So you've used a fixed room size for all of your experiments. Do you have any idea of how these results would change with these parameters?
Not in this particular study. No. We just we just explored this limited case and just varied slightly the dimension of the room in the assessment with respect to the training, but in the testing, the training, but not really a complete range of different situations. No.
Thank you.
Okay, so we have one last question from online. The question is, usually the generalized cross-correlation is defined using the expectation operator. So why did you drop or this, or why don't you perform temporal averaging?
We perform temporal averaging. Actually, these results are averaged results. Yeah.
Okay.
Yeah, maybe I forgot something on the slides, but it is
Great.
average.
Thanks.
Thank you.
Thanks to speaker again.
Thank you.
Thank you very much.